Hello students, today we discuss about analytic functions in complex analysis. First we discuss about differentiability of a function of a single complex variable. Let f be a function from C, the set of all complex numbers, to C. Let f C to C be a function defined by fz equals to w. Here z is independent variable and w is dependent variable. Both are complex variables belong to C, the set of all complex numbers. Now, fz is said to be differentiable if limit h tends to 0, f of z plus h minus fz by h exists. So this is number one. This is as we did in real analysis, and it is denoted by f dash z or d dz of fz. Here one thing I want to mention, that h is a complex quantity. I did not mention here. Here h is a complex quantity. H is not any real number. H tends to 0 complex number. Next, let D be a domain of fz. That is, we are considering now a function from D to C. Here D is nothing but a subset of C. If fz be derivable at z belongs to D subset C, then we can write from epsilon delta definition of limit f of z plus h minus fz by h minus f dash z equals to epsilon, where epsilon is a small positive quantity as we did in our real analysis, which implies after simplification if we multiply throughout by h, we get this thing, f of z plus h minus fz equals to h into f dash z plus h into epsilon, where epsilon is a function of h tending to 0 with h. Epsilon is a function of h tending to 0 with h. Next, differentiability and continuity. As in real variables, we may show that differentiability implies continuity, but not conversely. We did it in a real analysis. We know very well that in a real analysis, a function may be continuous at some point in its domain of definition, but it may not be differentiable thereat. But once a function becomes differentiable at some point in its domain of definition, it must be continuous thereat. Here, like thing we can observe. Here we write f of z plus h minus fz equals to, we divide by h and multiply by h. If f is derivable at z, the point z belongs to D, then limit h tends to 0, f of z plus h minus fz may be written as using this line, limit h tends to 0 f of z plus h minus fz equals to limit h tends to 0 f of z plus h minus fz by h into limit h tends to 0 h. That means we take limit h tends to 0 of both sides of this equation. Because f is derivable, we mentioned here, so this thing will be f dash z and this thing will be 0. So ultimately we get 0. So from here we can write limit h tends to 0 f of z plus h equals to fz. Simple. Which implies f of z is continuous at z. This is the condition of continuity we know very well at the point z. So what you get here? Differentiability implies continuity, because we assumed fz was differentiable earlier and here we got fz is continuous. So differentiability implies continuity. But continuity does not imply differentiability. To show this, we consider an example next. Here we considered an example to show that continuity does not necessarily imply differentiability. Here we consider a function fz which is z bar equals to x minus iy. That means we considered z equals to x plus iy standard. Now at z equals to 0, modulus of fz minus f0 equals to mod of z bar minus 0, because f of z equals to z bar and we know mod of z bar equals to mod z. So mod z, and here we consider less than epsilon. Epsilon here is small positive quantity, epsilon is a real quantity, and again we can write when mod z minus 0 less than epsilon, because here we get mod z less than epsilon. So here we manipulate a 0, mod z minus 0 less than epsilon equals to delta. Say we are going towards epsilon delta definition as we are very much habituated in our real analysis. Clearly fz is continuous at z equals to 0. From here this is very obvious that fz is continuous at z equals to 0. Now let us check whether it is differentiable at z equals to 0 or not. For that, here we write f of 0 plus h minus f0 by h. One thing you should remember that h is a complex quantity, not a real quantity. So this thing will be equal to f of h minus 0 by h, and fh, since fz is z bar, so fh will be h bar by h. Let h equals to p plus iq. Then h bar will be p minus iq by p plus iq. Okay. Now f dash z, which is limit h tends to 0 of this thing, that means f dash z means here fz 0, f dash 0 at the point 0. So limit h tends to 0, h bar by h equals to h tends to 0, because h equals to p plus iq we considered. So h tends to 0 means limit p comma q tends to 0 comma 0 p minus iq by p plus iq. Clearly, this limit does not exist. I will show you why. Which does not exist because if we set q equals to 0 and let p tends to 0, the limit becomes limit p tends to 0. Here we set q equals to 0, so this 2 becomes 0, limit p tends to 0, p by p equals to 1. Whereas if we set p equals to 0 and let q tends to 0, that is when, see, when q tends to 0, when q equals to 0, when we set q equals to 0 and allowed p tends to 0, this p approaches to the point 0 along x-axis, because p, q are two real numbers. So this limit happens along, this limiting process happens along x-axis. But when we set p equals to 0 and letting q tends to 0, this limiting process happens along y-axis. That means when p tends to 0, this is the process, p approaches to 0, here is 0 number, 0 complex number. When q tends to 0, q tends to 0 along y-axis in this way towards this point. Okay. So if we set p equals to 0, this limit becomes, just put p 0 0 here and get limit q tends to 0 minus iq by iq, I cancel out, qq cancel out, which is minus 1. So earlier we got plus 1, the limiting value was plus 1, here we got minus 1. So these two are not same. So we obtain two different values. Next. Now let us take some problems. Here we consider two problems. Prove that the function fz equals to mod z square is continuous everywhere but nowhere differentiable except at the origin. Okay. Solution. Here fz equals to mod z square, that means x square plus y square, where z equals to x plus iy. Now f dash z equals to limit h tends to 0 f of z plus h minus fz by h equals to limit h tends to 0, mod z plus h whole square minus mod z whole square by h, and by applying simple properties of complex numbers, mod z square equals to z into z bar, we know very well, limit h tends to 0, z plus h into z bar plus h bar minus z into z bar by h equals to limit. After multiplication, z bar will be cancelled out, and we get this thing z bar plus h bar plus z into h bar by h. Okay, equals to, see, h tends to 0, so z bar, limit h tends to 0 of z bar will be z bar, and limit h tends to 0 of h bar will be 0, plus limit h tends to 0 z here, because z is a constant, z will be treating as constant because here h tends to 0, h bar by h. Okay, equals to z bar plus z into limit h tends to 0 p minus iq by p plus iq, where h equals to p plus iq. And we have just showed you in the earlier page that this limit does not exist. We just show you this limit does not exist. Therefore, we can write, since limit h tends to 0 p minus iq by p plus iq does not exist, therefore if dash z does not exist for any z, but one thing, for any z not equals to 0. Why I put not equals to 0? Because if z becomes 0, here we considered if dash z. If z becomes 0, this factor will be 0 and this will be 0 total, and in that case if dash z exists, so if dash z does not exist for any z except 0. And the continuity part is very easy, because If z equals to mod z square equals to x square plus y square, which is a polynomial in x and y, second degree polynomial in x and y, homogeneous polynomial, and it is easy to say that it is continuous everywhere in the arrogant plane. That is why we write which is continuous everywhere in the arrogant plane. Okay, so we are done. Next we consider another problem. See, here you consider a function. It is a function of a complex variable. F z equals to x cube y into y minus I x by x to the power 6 plus y square. Z not equals to 0, because if z equals to 0, x and y both will be 0, and in that case function, the denominator gets 0, then function will be undefined. For that, f0 is defined separately, f0 equals to 0, and we have to show that fz is not differentiable. Fz is not differentiable at 0. Okay. Solution. At z equals to 0, f dash 0 can be written as limit z tends to 0 fz minus f0 by z minus 0, because there is a alternative definition of derivative and I applied that definition, which is equal to limit z tends to 0, fz means here x cube y into y minus ix by x to the power 6 plus y square into x plus iy. I just put the value of fz from this here, and f0 is 0, it is given that f0 is 0, and z is x plus iy, z is x plus iy. Now, we can consider this limit in two ways to check whether this limit exists or not. See, first let z tends to 0 along the line y equals to mx. That is, so we are approaching 0 complex number here along the line. This is the equation of y equals to mx. So Therefore, z equals to x plus iy equals to x plus I mx. Clearly, as z tends to 0, x tends to 0. Therefore, this limit will become we just put it a bracket here. So, this limit now becomes limit x tends to 0, x cube mx, just put mx in place of y, mx minus ix by x to the power 6 plus m square x square x plus I m x. Equals to limit x tends to 0, x cube x will be, we can take x common out, x to the power 4 x to the power 5 into m minus I by x cube into x to the power 4 plus m square into 1 plus I m. This will be equal to m into m minus I into limit x tends to 0 x square by x4 plus m square into 1 plus I m. And obviously, this limit will become 0 equals to m into m minus I into 0 equals to 0. So, we get 0 if we approach along this line, y equals to mx line. Now, I will show you if we approach along different curve to the same point. Suppose we are approaching to this very point 0 along this curve. Suppose the equation of this curve is y equals to x cube. Okay, y equals to x cube. This curve also passes through 0 complex number. Next, so let z equals to 0 along y equals to x cube curve. Then f dash z will be limit z tends to 0 according to our previous definition of derivative, fz minus f0 by z minus 0, this is just equal to limit z tends to 0 fz by z, because f0 is 0, equals to limit z tends to 0 x cube y into y minus ix by x to the power 6 plus y square into x plus iy. Now, one thing to observe, z equals to x plus iy equals to x plus I x cube. Clearly, as z tends to 0, x will be tend to 0. Put it under a bracket. So, this limit now becomes, the limit was z tends to 0, now this limit will be limit x tends to 0 equals to limit x tends to 0. Just put x cube in place of y here, x cube into x cube into x cube minus ix by x to the power 6 plus x to the power 6 again into x plus I x cube equals to, now if it exists, see whether it exists or not, x to the power 6, here 2x to the power 6, so x to the power 6 will be cancelled out from numerator denominator, so half can be taken as common out, limit x tends to 0 x into x square minus I from here by x into 1 plus I x square. So, x will be cancelled out from numerator denominator equals to half, just put x equals to 0 here, x equals to 0 here, we will get I minus half I. So, here we get a different value. When we approached z equals to 0 point along y equals to x line, in the previous page I showed you, we got limiting value 0, but when we approach along y equals to x cube curve to the same point z equals to 0, we get a different value minus half I. So, clearly f dash 0 does not exist. Okay. In the next class, I will discuss about the definition of analytic function, the condition of a function to be analytic, and two types of conditions are there: necessary condition, which is Cauchy-Riemann equations, and sufficient condition, and the problems related to that topics. Thank you.